You kind of already talked a little bit about it, but non-ergodic side effects are easy to think about, as opposed to path, which we'll get into in a separate section. But we can look at the non-ergodic side effects when we have recordings at a site. So imagine one of those people from the coin flipping example that I gave the seismometer. They recorded many earthquakes. And we can improve the predictions for just the site amplification at that site using those site-specific recordings.
And that site amplification is is that VS term, right?
Yes, it was
Okay.
that VS30 term.
Because it's interesting, because it's simplification, because even though you're adding it, it's actually you're adding it in log space, which means it's a multiplication in linear space.
Yes.
I love log space. It's so cool. It's just that whole concept of log space where you can take things and nature kind of works in log space more than
Yes.
that. But I guess that's why it's an addition, which then becomes a multiplication in linear space.
Yes.
Okay.
So this top plot on the right shows residuals versus period. So each period you can think of as a different intensity measure. The smaller dots are within event residuals calculated for each earthquake. And the reason why they're within event is because we actually subtract not only the prediction, but we subtract any event-specific bias. So like if you have 500 recordings for an earthquake, you get the average value for that residual for that earthquake. It may be positive, maybe negative, maybe zero. And then you also subtract that so that these residuals include within them hopefully just the site effects, but there may be path effects in there also, which we'll get into in future slides. And then we can compute a site term, which is the darker blue squares that has some standard deviation or dispersion about them because of the data. Using this site term, it represents the bias of amplification at your site, and we can add that onto what the model uses. So this ergodic line, this green line, is what the site amplification model looks like in a typical ground motion model. In this case, it's SS14, or this Sayin and Stewart 2014. And you can see when we add this line, which is average around 0.5 to 1 or so, to this green curve, we can see the actual amplification at the site, which is going to be greater than what the ground motion model was predicting. But the general shape is there. But because we're no longer averaging over many sites, we actually have a site-specific value. We see these finer resolution features. For example, the local minimums, the local maximums, that may or may not be significant, statistically significant, but they're there for our site nonetheless, as opposed to the smooth model, which smooths over all of our sites, all of sites in the database that you use for ground motion development. So it stands that for site effects, a fully ergodic model would be one where you don't have any information for your site except maybe some predictor variables, so you just use this smooth curve. A fully non-ergodic model is where you have 1 million observations, where you have like 100% certainty that you know what the amplification at your site is. So it stands that the number of observations kind of is where will land you on the fully ergodic, fully non-ergodic spectrum for site amplification models you land. So this is just the site component of a ground motion model.
So let me ask you, sorry. So if you increase the number of, so let's go back to first these two plots. Okay, so this it's only one site, it's in LA. Okay, it's a very specific, and you've taken a lot of different earthquakes and recorded them. And kind of you see the trend, each quote unquote line is one event. So you have many earthquakes. And for each recording, you measure how far off is it from this green line. And you plot this. And so there's a bias that this recording, this site itself is, because the zero is, just below it, this site is always going to get bigger earthquakes or more shaking, or you think is going to get more shaking than what you predict. And so if you have enough data, you could say, hey, we start off with our prediction and say, but we've got a site here that is more. We don't quite know why, but we can statistically, and you'll figure out, you'll tell us why and how we can predict this offset here. And that's kind of what the residual does, is it just tells you what this offset is. Now, if you increase the number of, and so you may have a site that has the opposite. So by the law, just because the green is an average, you should have one that's exactly on the opposite side. And it doesn't need to go up and down. It could go below 0 at different periods, right? And so what does it tell me? That this site is constantly above 0 for all periods. It's always amplifying and not at all periods.
So it means that the general shape of the ergodic model matches the general shape of the amplification at this site. It's just the level of amplification is off.
Okay, it literally amplifies all periods.
Yes.
And so it might give you some ideas on the mechanism. Now, if I increase the number of recordings, so you've got the dark blue squares is your average, okay? Is the shady blue give you your variability or your?
So it's like the confidence that the blue square is correct. So the blue square, like the true value, will be somewhere in that shaded region.
Well, but it's not, because you got a lot of points above it and below it. So 84% of it, right?
Well, yes, 95%.
90, yeah, between 95%. Okay. And so now if you increase the recordings, you're assuming, or you're hoping, that confidence interval will get narrower and narrower, right? Or if you improve your model, and because this is a residual, so if you improve your model, then it's not just about, and so it's interesting because you're confident, your values, you may be right on. We don't need 1 million recordings to be able to get a good estimate of where it's going to go, but our confidence will be better and better. And so if you increase the number of recordings and you've got a fully non-ergodic, is the shady blue is going to go to 0, right?
Yes.
And the residual is then in the next step will go to 0 if you include. So the residual with respect to the green line doesn't go to 0, but the new, you're going to have this new curve, and then your residual with that is going to be 0.
Yes, and that's only assuming that the path and event terms in the ground motion model are also correct.
Okay, yeah, of course. You see, that brings back to what we're doing. Okay, fascinating. Okay, thank you.
Of course.